So hopefully you've gotten good at drawing Lewis dot structures following those steps. So see if you can go ahead and draw the Lewis dot structure for nitrogen trihydride. Now this may be a great time to pause the video, practice that on your own. And so hopefully you drew something like this. Hopefully you had thought about your valence electrons. Of course, nitrogen has 5. Each hydrogen has 1, so you had a total of 8 valence electrons. After you put in these 3 bonds, each bond is 2 valence electrons, so that's a total of 6. Hopefully you were thinking, okay, you had 2 more valence electrons, and so you put them on our atom that doesn't have the octet. And so as we're taking a look at that, what do we call those electrons up there that are not involved in a bond? Of course, those are our lone pairs. Those lone pairs of electrons, as you've probably been reading in your textbook, the Vesper theory, are going to affect the shape. And the shape of these molecules is super important, and we are going to talk about that. How about hydrogen monofluoride? Again, a great time to pause the video. Hopefully you came up with something like this. Hopefully you were thinking about your valence electrons at the start. Hydrogen with 1, fluorine with 7 for a total of 8 valence electrons. Once you put in that bond, of course that's 2 valence electrons, so that means you only had 6 left. Hydrogen is okay with only 2, so hopefully you gave the rest of those to fluorine. All right. And so as we start to take a look at these molecules, we need to think about their shapes. There's several different ways to describe their shapes, as you've probably seen in the videos and in the textbook. I like to keep it simple. So if the atom is in a straight line like that HF that we just looked at, it's linear. If the atom is bent, it looks like this. It's just not linear. And typically the reason this atom is bent is because there are some lone pairs of electrons up here. These lone pairs of electrons do take up space. And so as they're taking up space up here, you can just sort of imagine them there, they're going to be pushing the other atoms down. In other words, bending it. And that is our Vesper theory. But of course, when I look at it, it looks bent. You need to know trigonal planar. So that's in a triangular shape and flat. And so you could see triangular shape and flat. You're going to need to know trigonal pyramidal, also in a triangular shape, but poofed up like a pyramid in Egypt. And the reason, again, is because there's lone pairs of electrons up there. So they affect its shape. And then tetrahedral. You need to know what that one looks like. So it looks like so there's a central atom, and then 4 atoms around it, and each one pointing to the corners of a box. You do not need to know the bond angles. And so what determines the shape is the central atom and what's attached to it. Now there's 2 options for things that can be attached to the central atom. Other atoms or lone pairs of electrons. And both are going to need space and affect the shape. Especially those lone pairs of electrons. Because remember, electrons are negative. And so they're going to kind of repel from each other, and so they're going to take up even more space. So this is a little chart that I use to remember what the shapes are and to be able to figure out what the shapes are. So I just look at what's attached to the central atom. If there's only 1 atom attached to the central atom, it has to be linears, no matter how many lone pairs of electrons there are. And again, we're only looking at the lone pairs of electrons on the central atom. And so this is a chart that I use often in determining shapes of molecules. By the way, the trigonal pyramidal, typically always polar. Here's another chart that's in your textbook, as you can see. And so again, as you take a look, if we had CH4, that would be a tetrahedral shape, and trying to be shown in 3D here. and the bond angle here's 109.5. Again, you don't need to know the bond angle. But if we add a lone pair of electrons there, like NH3, nitrogen trihydride, it's going to sort of collapse your bond angle, making it 107. And then if we have something like water, where oxygen has two pairs of lone pairs of electrons, it's going to decrease your bond angle even more. And that's what the Vesper theory is. All right, now once we've got those molecules, those covalent molecules sharing those electrons, another thing we need to consider is the electronegativity, how the atoms are attracting the electrons. So it's almost like they're having a contest to see who can attract it more. If we have an atom like this blue one here with more electronegativity, greater in electronegativity, something like fluorine, it's going to attract the electrons towards it more than the other atom. So they're not sharing equally. And so what happens, here's another picture for you. And so what happens is if you look at the electronegativity difference, you can figure out if the molecule is nonpolar, polar, or ionic. That's really how we figure it out. And so if you take a look, CH4, and for your next test, you will get a table of electronegativity. C and H, you can take a look at their electronegativities and that they're sharing equally because there's less than a 0.5 difference. And so they'll be sharing these electrons equally. Of course, this molecule, think about its shape. Yep, tetrahedral. Now, when you have a larger electronegativity difference, about 0.5 to 2.1, and you have a molecule made of two nonmetals sharing 1, 2, or 3 pairs of electrons, it's going to be a polar molecule. So, for example, in this case, oxygen has a much greater electronegativity than hydrogen. So oxygen is going to pull on those electrons more. And you can see the hydrogen and oxygen that we were just talking about. We are only going to do it once. So there's oxygen. There's hydrogen. So that's going to be a difference of 1.4. So it is going to be a polar bond. Now, after you've determined if it's a polar bond, you can then determine if the whole entire molecule is polar. Polar, we're thinking about the Earth with the North and the South Pole, a magnet with opposite ends, a north and a south end. And so that's what we're looking at for these molecules. And so the first thing you've got to take a look at is the bond. Is there a significant difference in electronegativity, making them bond polar? Then you've got to look at the molecule. Is the molecule arranged in such a way that one end can have a negative charge with the more electronegative atom, and the other end can have a positive, slightly positive charge? Like, for example, water. And in water, since oxygen has such a higher electronegativity, it pulls on the electrons more, making this oxygen end a little bit negative, leaving the hydrogen end slightly positive. So we would also call that a dipole. And we often show that with colors. The other thing we can do, let me go back one second and show you. The other thing we can do is look at where these electrons are shared and who they're being pulled towards. Obviously, the oxygen end of this water molecule, so it becomes a little bit negative, leaving this end of the molecule a little bit positive. And so this happens for two reasons. One, we have a polar bond here. The electronegativity difference is greater than 0.5, and the molecule, the geometry or shape of the molecule allows for there to be a negative charge at one end and an opposite charge at the other end, making it a polar molecule. All right, can you draw phosphorus trichloride? And we'll go through all of those steps. So I just drew mine on paper here and stuck it in there. Hopefully you were thinking 5 valence electrons for phosphorus, 7 for chlorine, and you have 3 chlorine, so that's 21. So hopefully you were thinking, okay, I've got a total of 26 valence electrons. Once I put in my 3 bonds, 2, 4, 6, I've got 20 left, 20 valence electrons left. So I just start putting them around the other atoms. Now, then I check to make sure everybody has an octet. Just remember that if somebody doesn't have an octet, that's when you need to make some of those electrons a double bond. All right, so what would you say the shape of this molecule is? Hopefully you were thinking trigonal pyramidal, and it is. Now, does it contain polar bonds? Well, let's look at the electronegativity difference. And then does the shape lend it to having opposite poles? So, of course, chlorine is 3.16, phosphorus 2.19, got a difference of 0.97. So, yes, these are polar bonds. Chlorine is pulling on those electrons more. So, if we draw it, and of course, we know that this is going to be trigonal pyramidal. So, it's actually going to kind of look like a triangle, so we're going to have that phosphorus at the top with its lone pairs of electrons. And then the 3 chlorines, so it's going to be kind of like that in that trigonal pyramidal shape with this end, that's a P by the way, with the chlorine end being a little bit negative and the phosphorus end being a little bit positive. And so it is a polar molecule. And of course, we already mentioned the shape. We know it's trigonal pyramidal. All right, couple quick little review questions. Which compounds have low melting points? Hopefully you were thinking covalent, like sugar. And that is where we need to stop. I hope this helps you as you're working through these covalent molecules.